I can stop my video. Okay, so everybody can see the screen. Now I can see my Zoom window. Okay. Chat. Yes, okay, here's the chat thing, good. Okay, Alex, let me know if at some point I become inaudible or there's a problem. Okay, so the paper is WormSpace, modular foundation for simple verifiable distributed systems. This paper appeared in SOC 2019. SOC is Symposium on Cloud Computing Systems, a conference on that. So here are the authors. This is from Yale. Mahesh Balakrishnan is now at Facebook. He is, I think, the person responsible for the consensus part. And there is also a formal verification part. I think Zhong Shao is responsible for that, a faculty at Yale. And for this presentation, I'll be focusing on the consensus part and not on the verification part. If there is interest, a breakout session can discuss the verification part. Okay. So this paper is about WormSpace. It's about introducing the WOR abstraction, write once, register abstraction, as a first-class system building abstractions for distributed systems. WOR provides a single-shot consensus via data-centric API. By data-centric API, we mean read-write operations to access these registers. This acts as a building block for applications that and provide applications durability, concurrency control, and failure atomicity. So we are interested in this paper because for the beginning, we are reading papers about Paxos. Last week, we looked at Griff. And here the WOR, each WOR instance is implemented via Paxos instance. So it's not the write once register feature comes from using Paxos, and it abstracts. The WOR provides an abstraction of Paxos for higher level system primitives and higher level applications to build upon. Okay. So the WormSpace is the name of the general framework. It stands for write once, read many address space. The WormSpace organizes the address space of the WORs into segments called WOSes, write once segments. So WOS is a sequence of WORs. WOS is a sequence of WORs. We can already see that a sequence of WORs is a good abstraction to impose a total order, to provide a log abstraction, to provide state machine replication on top. And we can even go lower level primitive using the WORs, not the sequence, but set of WORs to keep decisions taken by participants in a two-phase commit protocol. Okay, so here is a high-level figure of the system. So these are the write one registers, and they are grouped into WOSes, right? And many of them, it just shows 3, but you can think of many grouped into a WOS. A fixed size is grouped into a WOS. This is implemented over Worm servers. These are replicas that store the registers, the WORs, through Paxos. And then to interface with the application on top, a client can allocate a WOS and become the point of contact for the application for example, state machine replication, for example, acting as a log sequencer, or a two-phase commit participant, okay? So there is trimmed. Trimmed means that maybe the application is done with these logs already, so it doesn't need them. Trim is something like delete, so those are gone, garbage collected, if you like. Written means that you write to these WORs inside WOS. And unwritten means that something happened. Maybe the node that captured the WOS had a problem. The consensus did not complete, and another node can capture and invalidate that WOR, and that will be skipped. And there is also unallocated. We are going to talk about this next, because first you need to allocate a WOS, and then other clients, you can allow other clients to capture WORs inside an allocated WOS and write to them and read from them. But first you need to allocate at the level of a WOS. Okay, this provides some structure and simplifies management and batches things, and you can also make the client to be a sticky client and do this in batch fashion. So the paper shows that the WOR abstraction, the WormSpace framework, is useful by building 3 applications on top of this. One of them is WormPaxos, which is a Multi-Paxos implementation over the WormSpace. The other is WormLog, a distributed shared log implementation on WormSpace. Finally, Worm transaction is a distributed fault-tolerant transaction coordinator implemented on top of the WormSpace. And the paper shows that they have performance comparable to the performance of native or custom implementations of these applications. Okay, what is the value proposition of the WormSpace? What is the value proposition of the WormSpace? There is no new algorithm presented here. It presents a framework. But what is the value proposition here? The value proposition is that this is an abstraction that makes life easier for developers using this abstraction. Developers do not need to reason about or understand Paxos protocols to build applications on top of the WormSpace. I mean, applications are very useful and very powerful. We know MapReduce, right? I mean, MapReduce operation is a simple operation, but the MapReduce abstraction, the framework of MapReduce Hadoop, made the data analytics applications flourish. Similarly, Spark took that further. And these abstractions does not have to be at high level. Spark is pretty low level. It gives you many operations that you can customize, similar as in TensorFlow. So WormSpace could be such a thing for applications that require coordination. So I like the paper a lot because of this, promise, because of this value. And yeah, so I already mentioned this, but since WormSpace API is at a nice level, it's not at a very high level, not very low level. It's at a nice level. So it enables building optimized designs on top of it. I think a demonstration of this is at the WormTX, Worm transaction application. So we will see how we can use this API more efficiently at a lower level to provide more performance to the system, okay? But it's still at a good level that the developer does not need to rewire communication pattern. It uses this WOR API for a data-centric API to accomplish what it needs, okay? So I mentioned Mahesh. Mahesh has been working on consensus systems. He was involved in the Corfu paper, etc. He's responsible for the consensus part of this paper, I think. And he's right now at They have been working on building the loss storage system for Facebook's control plane. Hit this link after maybe the presentation because it's a really nice explanation of some of the ideas in this paper put in practice to manage Facebook's large-scale needs. The paper also has a formal verification track. The formal verification, it's like 1/3 of the paper, but I'm not going to discuss it in the presentation because it's sort of like separate, and I think it would have been better if the paper just focused on the systems and consensus track and elaborated more on that, because the formal verification track is like a parallel paper, and sometimes giving one idea per paper works better, you know, investigating that idea in full extent and focusing on one thing per paper. But if there is interest in the breakout session, this is something a breakout room can discuss. So here the idea is that they also provide reuse of the WormSpace proof for the applications that are built using WormSpace. For this, they use certified concurrent abstraction layer method. But yeah, we are not going to be discussing that. Okay. Good so far. Maybe in the chat, some indication that you guys are still awake. I think there are some people from connecting from India. It's very late there. So I'll try to keep this short. Okay. So WormSpace system is built on WORs. It uses the write-once segments on top of WORs. The address space of WORs is organized into WOSes of fixed size. WOSes are explicitly allocated via an allocation call made in a segment ID, and this succeeds only if this segment is not allocated. So this is important. I think the paper did this nice because for WOS, it uses the allocation word, allocation concept. For WORs, it uses capture context, okay? When I say capture, it's capturing a WOR inside of an already allocated WOS, okay? You allocate WOSes, and then you can capture WORs inside that WOS, okay? So you first, a client first needs to allocate a WOS, which consists of many WORs inside. And once a client has allocated a WOS, any client in the system, this gives us flexibility in building applications on top, can operate in this WOS by capturing WORs in this segment, in this WOS, okay? So what can the client do in an allocated segment? It can capture a WOR, it can write to a captured WOR, and it can read the WOR. Okay, now the capturing of a WOR and writing to a captured WOR maps directly onto Paxos phase 1 and phase 2. In other words, these guys are implementing the distributed write-once register concept using the Paxos algorithm. Okay. High-level way of thinking about the WOS and WormSpace is to use the distributed key-value connection. WormSpace design is similar to a write-once distributed key-value store. I emphasize write-once because in most key-value stores, you can update the key many times to write in a new value, replace the value there. Here, the keys are write-once, okay? Because the keys are 64-bit IDs that are WOR addresses, okay? And this 64-bit ID is created by concatenating the segment ID, which comes from the WOS, with the offset of the WOR within the segment. So this is how WORs are mapped to the partitions. And each partition, meaning we are partitioning at the level of WOS, each partition is in turn mapped to some replica set of WORM servers. Yeah, partitioning occurs at WOS granularity. To perform an operation on a WOR within a WOS, the client determines the partition storing the segment by using a modular function to figure out which replica set it needs to contact to capture the WOR using Paxos phase 1 and to write to the WOR using Paxos phase 2. And this write may not succeed if another client can also capture the WOR between these two operations, between the capture and write operation. Okay, so I already mentioned this, but this is how we enforce the WOSes and WORs, the right one's nature. The client-side library layers the logic for enforcing the right one segments. Each WOS segment is implemented via a set of data WORs, a single metadata WOR, a single metadata for the segment that's also kept as a WOR, and a single trim WOR to say that is this garbage collected, trim is the delete of a WOS. Allocating the WOS requires writing to the metadata WOR. This is done through Paxos. And next we are going to discuss how do you capture and write to a WOR. But metadata of a segment is just the first WOR maybe in a segment, okay? And if two clients race to allocate a WOS, the first one to capture and write the WOR wins. The nice thing about Paxos is even in an asynchronous environment, Paxos is safe. Paxos is not going to make two clients, two agents win. And in a partial synchronous model, Paxos eventually makes one of the nodes win and terminate the consensus. Okay, that was how you allocate a WOS. Now we are going to talk about how do you capture a WOR. So the clients must first capture the address before writing to it. The clients must first capture the WOR before writing to it. The capture call is similar to phase 1, the prepare phase of Paxos. The lock must be acquired to write, but it can be stolen by others. So this is Paxos refresher, Paxos phase 1. Can I lead you with this pallet number? Yes, etc. This is the capture call for a WOR. Then if nobody else captured it, you write to the WOR in parallel to the replicas and they say, okay, and then the write is successful. The read is similar. The read is similar to phase 1. If it is already captured, it reads. And we are going to discuss if the read sees a partial values, the read then goes to phase 2 to complete that partial values. This is like in Paxos where you learn the suitable value and you rewrite the suitable value to complete the Paxos. Okay. Okay. Most of the time things will work okay. You will be able to capture and then to write to what you capture. A successful capture call returns a unique non-zero capture ID. This is the 64-bit ID that I mentioned earlier. A subsequent write by the same thread is automatically parameterized with this ID to reach there and do the phase 2 of Paxos. The write call succeeds if the WOR has not been captured by some other client in the meantime, right? Because I captured here, then I go here. Let's say another client, due to something, due to some miscoordination, etc., captures it. When I try to write, the replicas are going to tell me, as in phase 2 of Paxos, that nope, you're not my leader anymore, right? So either I can go to phase 1 to capture and try to write again, or maybe timeout, try after some time. Okay, but the nice thing about Paxos is it is safe even under multiple leaders, so this will be safe. And then a read operation may also learn partial write that did not reach a majority or not all the nodes, and may help to fix that by going to phase 2. It's Paxos. So, okay, I talked about this, but here is to recap what I said. Each WOR is implemented via single-shot Paxos consensus protocol with the WORM servers within a partition acting as a set of acceptors. A capture call translates to a phase 1A prepare message, whereas a write call is a phase 2A accept message. Read operation mirrors the phase 1A message, but if it encounters a half-written column, it completes the write. Each WORM server maintains a map from WOR IDs to the acceptor state for that single-shot Paxos instance. This is the distributed key, write once distributed key value link. If a map entry is not found, the WOR is treated as unwritten. Okay, so that's it. That's the WormSpace. Now we are going to talk about 3 applications that's built on top of this abstraction of WORs and WOSes. So this is straightforward use. This is a Multi-Paxos application built on top of the WormSpace. This figure is familiar. Now our client is a leader of a Multi-Paxos, and we like to have a stable leader, at least for the WOS. And this is maintaining, the application here is maintaining a state machine replication, so you don't want to change the leader too much. So one client can first allocate a WOS, okay, and then do writes to the WORs inside that in sequence, and this becomes our SMR log. And we can have learners by other services by just going to the sticky leader to learn them. This is fault tolerant because the log is replicated over 3 replicas. If the leader dies, or if one of the replicas dies, a new leader can be elected. A new leader can either complete some of the half rights, and then but because this leader has already what's the called word allocated this, it may write incomplete, or it may nullify them by writing no op to the rest, and then it can allocate the next WOS and do the same thing to maintain an SMR for the system. So this is the idea for WormPaxos. So to recap this, servers that wish to replicate state act as WormSpace clients. These are called WormPaxos servers. They can propose new commands by preparing and writing to the next free address in sequence, learn commands by reading the address space in sequential order. WormPaxos server becomes a sticky leader simply by using a batch capture on a WOS. What does batch capture mean? Batch capture means that I allocated this WOS, but instead of trying to do a capture for each WOR in sequence, I'm a stable leader. I can do a batch capture. I start all of the capture operations on the WORs inside this WOS at the same time, so I don't incur the latency delay anymore. Does this make sense? This is called a batch capture. And then toward the end of maybe this WOS, I can allocate the next WOS as the leader, sticky leader of this thing, and I can do a batch capture on the next WOS, so my operation becomes smooth. Basically, this is Multi-Paxos, where this part is done in batch manner for the sequence of the log coming up, and then all I do is this one, phase 2, right? Write it and wait for majority, declare it written, send the acknowledgement for the write. What if the leader crashes, this sticky leader crashes? This is the client of the WormSpace. A new leader that allocates the next WOS can batch capture the WOS of the previous leader, complete partially finished operations, and fill in junk values to unwritten WORs to prevent holes in the SMR log. Okay, I'm starting the next application. This is the worm log. Maybe the Delos system in Facebook is a log system, maintaining a log over Paxos instances, so it would be relevant to this. Again, the worm log is very simple. It's very, very simple. This is similar to chain replication, but now instead of in chain replication, where the replicas needs to be done in sequence, we can do all the replicas in parallel, right? This is also like Multi-Paxos. The one node becomes the client, the sequencer. It does a allocation of the WOS and always allocates the next WOS as it's coming close to the end of this WOS. And it does a batch capture on all the wars. And then it sends these tokens to the clients, because the clients will be hitting the sequencer to say, tell me the tail of the log. I want to write something to the log. And then this guy already did the batch capture, so it's giving the next wars token the ID, 64-bit ID, so that the client can write it. And this will be, again, phase 2 of Paxos. This will be just one round trip. And this is pretty streamlined. In chain Paxos, you need to do sequential replication, but here you are doing parallel replication. So this is done in one round trip time. Okay, so there is a comparison to Corfu in the evaluation. Now I'm skipping to the next application, worm transaction. We all know that two-phase commit has a blocking problem in the presence of crash failures. The worm transactions build on WormSpace and leverages it to make the two-phase commit non-blocking. Okay, and the paper shows a variant of protocols to show how the efficiency of this could be gradually improved. So here is the most straightforward protocol. The transaction manager is contacted. The transaction manager contacts the replicas for their WOS. The replicas uses the wars. First allocate a war, then write the war its vote, and then sends the vote to the transaction manager. Why do we do this first? Because if I die, the system does not get blocked. The TM can learn it from the war and decide on the correct thing. Or even if the TM changes, the new TM can learn it from the war and give the correct commit or abort decision, and the agreement is not violated because my vote is persisted, and anybody comes later on can see the same value and will come to the same decision. So this is the very basic transaction, two-phase transaction implementation over WormSpace. Okay, let's improve on this. This is 8 message length: 1, allocate, write, vote, commit or abort. If the clients allocated in advance, like batch allocate for their votes, they will just do a write. So we shaped 2 messages from A8, now we are B6, okay. Okay, the next thing is to say that why is the client reading from the war? The transaction manager can read from the war itself. So we say one more message because the war sends to the replica sends to the TM. Let the TM read directly from the war, okay? The next thing is, well, let the RMs read from each other's wars directly. So the TM is used only to start the transaction, but then everybody writes to their war and everybody reads from each other's wars to decide if this is commit or abort, okay? We can even take this one more step, saying that one of the replica, instead of contacting the transaction manager, it starts the transaction by asking the other replica. It uses its war. It reads from the other's war. The other reads from its war, and this can be done in 3 message delay. This is impractical one. This is saying that if they knew to start at the same time, we can theoretically do this in two cases. So what does this worm transaction application show? It shows that the WormSpace can be used at a lower level to provide coordination to provide efficient coordination to other system primitives. And an important system primitive is a distributed transaction system primitive, and that's the idea. Okay, I'll go to the evaluation. There is some micro benchmarks for read and write. Read and write is the same operation actually, right? Because it's phase 2 and phase 1, but it's just one round trip. But if you need to do capture and the write, then your throughput will be half as the throughput of just do a write if you had batch capture. So that's what this shows. This shows that WormPaxos does much better than CPaxos and ePaxos. But here's the thing. I mean, this assumes that the CPaxos does not use the stable leader optimization. Every time phase 1, phase 2, phase 3 is done by CPaxos. On the other hand, the WormPaxos uses the Multi-Paxos stable leader optimization. It only does phase 2. If the CPaxos also did phase 2, it will be very similar to the WormPaxos performance. And again, the figure 10 is the corresponding throughput chart for figure 9. But again, for CPaxos, this is not using the Multi-Paxos optimization, whereas for WormPaxos, it uses the Multi-Paxos optimization. This is the worm log evaluation. This is Corfu, little sad looking plot because it's using, because of overheads, I think many overheads there. But the paper shows that Paxos War just implements chain replication and gets the same throughput as that. But its latency is half of that of chain replication. Why? Because while chain replication needs to do in sequence, the Corfu, the WormPaxos can do these things in parallel with respect to the 3 replicas of the war. Okay. Finally, this is the worm transaction showing that by each improvement we can cut the latency. Okay, so that concludes my presentation of the paper. It took 30 minutes, but we can go to the general discussion. Okay. So I stopped the sharing. You can unmute yourselves. We can go to the Google Docs. We can read the questions from Google Docs. We can answer some of the questions, and feel free to chime in with your own questions. We don't have to follow the order from the Google Docs. Actually, let's do this. Okay, here is the Google Docs. You have the Google Docs link from the Slack channel. But maybe I'm sharing it so we can all look at the same one and discuss. The first question is by Alexi. So I will just read the question, tell you guys my answer. And then if there is any feedback, we can discuss that. And then before going to next question, maybe if there is question from audience, let's wait for that to be asked and answered. So Alexi asked that write-once registers are not new. They have been explored in the literature before. For example, Heidi Howard's generalized solution to distributed consensus builds on top of write-once register abstraction. Are there any other systems papers that take Paxos protocol into this write-once space? And how does WormSpace use of register compare with the generalized solution? So The WormSpace implement the WOR via Paxos, as we discussed. Heidi's work assumed the WOR is provided at the middleware level at each node at the middleware per node, not in a distributed way. And then Heidi's work built the Paxos protocols on top of this write once register per node level. This simplifies the Paxos protocol, and this also makes it easy to write Paxos variants. But the idea is that WormSpace implements WOR, the write once register abstraction via Paxos, whereas Heidi's work at middleware level implements the write once register and shows how we can build Paxos protocols easily on top of that. So WormSpace registers are distributed registers. Heidi's registers are local implementations. Heidi's registers also have the nature of many rounds per register. This should be provided by middleware. This can get a little tricky, the many rounds. How do you know where to stop? How do you allocate that? That may get tricky for a industrial implementation. So yeah, that's my answer to the comparison. Are there any other systems papers that take Paxos protocol into this write once space? There may be, I'm not aware. Yeah. So anybody wants to add something to this? Okay, then we wait for a question from the audience for the before going to the question two.
Hi, I have a general question. I mean, I think I'm missing something here. So because WOS is a sort of an abstraction, and below it is assumed there are some sort of replicas. And so considering that it is built on a Paxos instance, so there should be, if there are F failures, there should be at least 2 F plus 1 replicas. Am I right in considering that fact?
Yes, yes.
Okay.
So I guess saying that they deployed this with 3 replicas. Each WOS is replicated over 3 replicas, and one of the replica can fail.
So considering in the general Paxos or any other consistent environment, when a primary is, I'm assuming the case of sticky leader, I mean, assuming there is a primary. If the primary fails, the other replicas are able to detect it and they start a primary replacement algorithm.
Yes.
In this case, I'm just curious, who will be starting the primary replacement? How, if the primary does not get a majority, and there's a way in which either primary sends a decision, final commit to everyone, or we can skip that phase and we can basically have like all the replicas acceptors send decision to every acceptor basically, and then they can, if they do not get majority, they can say, hey, the primary is bad. So how will this thing happen in this case? I'm a bit confused about.
Right. So here the replicas are just acceptors. The leader comes from outside the system. It's a client of the WormSpace. In Multi-Paxos, the client was a sticky leader. It did a allocate of a WOS and then batch capture on the WOS. But if this sticky leader, if this sticky client dies, your application should have a way of selecting another client to allocate the next WOS, and this new leader, so to speak, because there will be only one guy who would be able to allocate the next WOS, because it's also done by Paxos through the metadata WOR on the WOS, and this client, it would be this client's responsibility. Again, this is the code you need to write to go to the previous WOS and either complete some of the WOS which are incomplete by learning the suitable value and rewriting it back. And if there are WOS that do not have anything written, it will write no operation on top of them, so that those are basically in the SMR log, those show up as no ops. Does this answer the question?
Yeah, I think, thank you. That makes quite sense. Thank you.
Okay, we go to next question, maybe take another question after this from the audience. Alex Miller asked, WormSpace proposes WOSes as the fault-tolerant replicated base on which to build applications and services. Other work, Tapir, replicated commit, etc., suggests that replication should be fused with higher level protocols applications for maximum performance. Yes, there have been indeed several works like this, Tapir, replicated commit, maybe rifle, etc. Replication should be fused with higher level protocols applications for maximum performance. Does WormSpace 3-message delay 2PC show otherwise? Yeah, this is a good question to discuss at the breakout rooms, maybe to, because, yeah, he also mentioned this for the, no, this is another one, but I guess we can also copy this for the breakout room discussion, because this is a good in-depth question, maybe if we want to use it for breakout sessions. So my general answers is, you can have more performance by going lower level. The WormTX example application showed that WormSpace can be employed at a pretty low level, right? It's not at the Zookeeper or ref layer. If you look at Paxos, Paxos was packaged to us previously at Zookeeper level, which is a big, very, very coarse grain, right? Or you could employ Paxos as a protocol layer, ref layer, but it's like a white box approach. You are basically, this is not giving an abstraction to the application. The application developer needs to do all the task of wiring this raft consensus to build the application almost from scratch. But this gives an abstraction using read-write and hides the complexity of Paxos at the word level, and it can be still pretty low level, as we have seen in Worm transaction. I think the interesting question maybe for breakout session is, you know, which is a better way of doing things, right? I mean, giving the replication, or sometimes even out of order replication, and building the high level applications on top of that for maximum performance, or building on this on top of that. Yeah. Anybody want to add something, Alexei?
Yeah, actually, as a matter of fact, I don't really think that this is on a different level, because if you look at, for example, this WormPaxos, right? All it does, it shifts who is the leader of this Paxos to the client. So it actually, it's not on a lower level. It gives more of this underlying reliability, fault tolerance of this replicated storage, whatnot, WormSpace, to the application level. But the application is driving a lot of the processes. The WormPaxos is implemented at the application level. So is the transaction, Worm transactions, they are and logs, they're implemented at the application level with the help of this underlying hidden Paxos API and allocation of worm spaces and things like that.
Okay. Anybody else who wants to add something? Going once, going twice. Okay. So yeah, let's get to the breakout rooms maybe quickly. Suyash asked, I'm curious, what is the purpose of a WOS? WOS is at a coarser granularity than the WOR. It supports some batching, and also it supports batch capture, which improves the performance. How will the proposed design get affected if there was no notion of WOS? I think, yeah, we would lose performance. We would lose performance.
Essentially, you'll have to do the two phases of Paxos for every single registry you try to write.
Yeah, right. So this is like a hierarchical thing. When you allocate the WOS, maybe you can also do the batch capture in advance as well, so that you keep things, you know, pretty performant.
But the curious point here is because every client does not need to write to every var. So I mean, in some vars, if there are, say like 10 var, and a client only needs access to one var, and say each client only needs access to one. So capturing a vars did not actually solve any problem. It just is sort of an allocation which created a metadata. The client, for the first client who came, he allocated some metadata and he captured this, allocated this vars, and now he's just going to use one of the vars. So next, all the clients who come, they're still going to use WOS. I believe it all depends on the application, isn't it? If the application requires a client to use multiple WOS at any point of time, then a WOS is more useful.
Right. This is not assuming probably a very malicious environment. So actually, if you look at the worm log, what happens is sequencer captures and then each wars in sequence and then gives them to the clients one by one. I mean, a client can do another capture on top of that and basically ruin performance. But this is assuming like collaborative clients. This is not assuming an adversarial environment to build with, and this gives a batch operation level to do on top. I guess if you want to even make that more robust, you could say that you could have different type of WOS maybe where you allocated, you preempt any other client to maybe capture a WOS, capture a war inside the WOS. I don't know, but it's given mostly as a performance improvement clustering on top of WOS. Anybody want to add? Yeah, I see what you're saying, but this is assuming that not an adversarial, but a collaborative, cooperative environment to build applications on top. Okay. Basio's comment is on the same lines. What if you introduce hierarchy over war? WOS would belong to a higher level, more coarse WOS. I guess WOS is a hierarchy over war, if I'm not understanding this question. So it's, yeah, this would be mostly for performance. I think we discussed the figure 9 and 10. I already mentioned that this is not using the Multi-Paxos thing. Okay, let's decide on breakout questions. So breakout.
Professor, I just have one question regarding the log application, which shared log, right? So in the paper, it says that like when we implement it using this WOS model, so then the number of calls increases to 3, because one is when the application asks the sequencer for a sequence ID is 1, and then it gets the sequence ID and then it goes to write. So that is like 2 calls, so it increases to 3. So yeah, how does it like improve over the chain replication? Yeah. How is it better than the chain replication in terms of performance? In
chain replication, the 3 replicas would be hit in sequence, right? The configuration box would know this is the head, this is the intermediate, this is the end of the tail, and then it would send the call to here. This replicates, send the call to the next replica. It replicates, send the call to the next replica, the tail, and then the tail will say to the client to say that, okay, this is now properly replicated. Okay, this is done in sequence, but in the WormPaxos method, you hit these 3 in parallel at 1, right? Instead of 1, 2, 3, 4, you can do it in 2, going to all and getting the answer back. It cuts one round trip, right? Instead of, or it cuts two messages. That's what the paper refers to, saying that instead of n+1 RTT going through all these replicas one after the other, it's just 2 RTT. Oh, n+1 RTT is, wow, n+1 RTT is a lot. So this is basically assuming in chain replication. You go to this, he says yes. Then you go to this, he says yes. You go to this, he says yes. But this is saying in WormPaxos, we can go to all of them at once and get one.
So basically the tail, basically the optimization is the tail is found pretty soon and for the application to write.
The optimization is the replicas are contacted in a parallel way, and the tail is maintained by a sequencer which do a batch capture, and then it will be giving a token to whoever asks, which would be the next place to add the head of the log or the tail of the log to add. Yeah, the token is basically the 64-bit ID of the next war to the client. Yeah, the optimization is we do this in parallel instead of in chain replication in sequence.
Okay, yeah, thanks.
Okay, so we can do 30-minute breakout session. Breakout sessions are fun because we can discuss with a group of 4 in more detail, in more depth over one of the topics. So I guess we are not many, we are like 9 people, so we can have 2 breakout rooms. Let's choose which topics to discuss. Alex's suggestion is to continue immutability discussion. Immutable data structures, what are the advantages, disadvantages of immutable registers compared to other immutable data structures? Alex Miller suggested that WormSpace can be viewed as an easy-to-use Paxos as a library, with the many variants of Paxos that exist, which can be implemented using WormSpace's. Which of them can be implemented using WormSpace API? What extensions to WormSpace would be needed to be able to support the others? Right, so the paper says that, right? So in Multi-Paxos or with a stable leader, you get the WOS yourself and then you keep going. But it says that if you put a rotation, you can have something like Mencius, but you need to coordinate the rotation yourself, right, for Mencius. So the question next is, how could you do flexible Paxos? I don't know. It's a good question, yeah. Or how could you do ePaxos? Yeah, I think this is a good question. Let's make this definitely one of the discussion topics. Basically, select a couple Paxos variants and discuss how you would be able to, in 20 minutes, use the WormSpace API to implement that Paxos variant. Okay, this is my question, so I will be partial to this. Is it possible to add Paxos as a programming language primitive by using WormSpace as a programming language library? This would give programmers an even lower level primitive to use Paxos, and we can call this Lambda Paxos, as in Paxos on demand. Which programming language would be the most amenable to this, and how would we go about doing this? Does this sound good to you guys? I mean, the other thing is we could do formal verification. Is there any interest to formal verification discussion? You can use the chat to say yes. I need to open the chat to see. One person interested in formal verification. Oh no, that's a minus. That's a -1. Okay, sorry. Yeah, okay, so let's not do the form. Let's not do the formal verification. Is this too okay? Oh, this is also a good one, right? WormSpace proposes WormPaxos as default. Compared to replication on top or below, but as WormSpace can also be deployed at a pretty low level primitive. So what do you want to discuss as the second question? People discuss in one breakout room, question number 2, and in the other, either 3 or 4. 3 or 4, maybe you can write into the chat. Okay, let's see some more votes. Right now, 3 is winning. 3 is still winning by 1.
Can we double vote?
Is there a tiebreaker? Oh.
I'm okay discussing just one question, to be honest. It's not a lot of people that we have.
I think it's better when we cut into, I think 4 is a good number, 4, 5. 4 is a good number for the, okay. Okay, then I'll, so one of them is 2, one of them is 3. That's what we are going to do. Now, programming language, do we have enough knowledge about programming languages to carry out this discussion? I don't think I would want to, I voted for 3, but maybe I will change it because I don't know enough to.
What's up is the programming language. I mean, there is a primitive, right? There is an API that it already gives you, right? Get the war, capture, right. That's it. It's not a programming language thing. It's like a framework, the API thing.
So
you already have it.
Just having this at the library level would be enough to build applications. We don't need to go at the program.
Well, you need to keep it at the library level because you still need to have the distributed backbone for this. You know, it's not going to run by itself on a single machine without a distributed backbone.
If there is a program, there are a couple programming languages, guys, that says that, yeah, let's do 3. Let's do it. Otherwise, I change my vote to 4. Okay. So 2 and 4, we